This video we understood the Arrhenius concept of acids and bases and also discussed some of its limitations. So, in order to overcome the limitations of the concept, Bronsted and Lowry developed this concept of acid and bases. So, they pointed out that in any acid-base reaction, there is a transfer of proton. So now it's not H plus and OH minus hydroxyl ion or H plus ion. It is understood in terms of proton transfer. Okay. Now, how do we know a substance is an acid? If the substance is a donor of the proton donor. What is proton? Proton can also be understood as hydrogen ion. Okay, because hydrogen has one electron, one proton in the atomic state, and if one proton is removed, so it becomes H plus. So although we are discussing H plus, understand it in terms of a proton. So proton donor is an acid, and base is nothing but proton acceptor. So we are not defining base as dissociating into what you say OH hydroxyl ion like RMS concept. So we can just write an arrow proton donor this donates and this is proton acceptor. Okay, H plus comes to this. That is called a base. So now it removes the first limitation of RNS concept wherein H plus and OH minus ion dissociation is required to understand acid or base. Okay. Now we can say any molecular ion capable of donating a proton or transferring a proton is an acid, and any molecular ion that can accept a proton is the base. So let's take an example and we will see ammonia. Ammonia doesn't contain OH minus ion, so we cannot directly say it's a base based on RNS concept. But based on this concept, let's see the reaction between ammonia and hydrogen fluoride. Hydrogen fluoride is a strong acid. Okay, so let's say ammonia reacts with hydrogen fluoride and we get the ionic form first. So ammonia converts into ammonium ion NH4 plus and this hydrogen fluoride gives F minus. So again, NH3 plus H will give NH4 plus and F will be F minus. Now, because ammonia is accepting a proton, NH3 plus H plus, so we can imagine like this is converting into H plus and F minus, and this H plus is ammonia. So this is a proton acceptor. So this is 1 by NH4 plus. So ammonia can be considered a base. Correct. And similarly hydrogen fluoride is giving away the proton, so hydrogen fluoride is an acid. Okay, the best part is we are not treating this as dissolving in water, right? So we have not written water anywhere. Okay, there is no role of a solvent here. Okay, now let's take one more example. We can also take up a case where we are having uh, water as the solvent. To understand that Bronsted-Lowry concept also is able to cover the acid base definition as per RNS concept, but in a different way. That is by understanding transfer of power. Okay, so let's take that example. We already discussed that HCl when it is dissolved in water, so HCl was a gas initially plus H2O liquid, it dissociates into H3O plus, which is hydronium ion and chloride ion, right? This was understood in Arrhenius concept also. Now, this H3O plus ion, this H3O plus ion and chloride ion, which is what have come from HCl. So, if I say HCl plus H2O plus, it is reacting with a base ammonia. So, we are basically understanding acid-base reaction. So, this can be considered as H3O plus aqueous plus Cl minus. So I can write it as H3O plus aqueous plus Cl minus aqueous plus NH3. Okay. You can understand it like this. So I will not put an arrow mark because it's not a reaction uh, uh, which we are considering. We can understand it as when HCl reacts with is reacting with ammonia in aqueous solution. First step is this, and second step is that reaction with ammonia. So I will replace this left portion with this. So this is an intermediate step. So I will replace this with this, and it will give what? What does it give? It gives, so H3O plus, from that 1H plus will go to NH3. So there is a proton transfer, 1H plus to ammonia, and therefore it becomes NH4 plus ammonium ion, NH4 plus aqueous. And when 1H plus is removed from hydronium ion, it will give water, H2O. And then there is chloride ion. Okay, there is chloride ion. So here we can consider ammonia as accepting a proton, therefore ammonia is a base, correct? And hydronium ion is donating the proton, therefore hydronium ion is an acid, but this hydronium ion has come from what? HCl. Okay, so therefore HCl is an acid. Understood? So in this way, the acid and base definition of compounds containing H plus and OH minus, here OH minus is not there, but H plus can also be understood using Bronsted-Lowry concept. Okay, now similarly we take up a case of OH minus also. Let's say we have ammonia gas and it is dissolved in water. So ammonia NH3 aqueous plus H2O liquid. Okay, now there is a dynamic equilibrium because ammonia is a weak base. And what does it convert? 1H plus of water will go into NH3 because NH3 is a base. It will accept a proton, right? So it will form NH4 plus aqueous. And what does water become? Water becomes hydroxyl ion, OH minus aqueous. 1H plus is the. So we can understand the concept of arrhenius, wherein compounds having H plus or OH minus were understood as acids or bases using the concept of Bronsted-Lowry. But here we have to understand that NH3 is accepting a proton and H2O is donating a proton. So NH3 plus is a base which is accepting proton. H2O when converts to OH minus, it is a acidic reaction. Okay, it is donating a proton. Similarly, HCl donated a proton, so HCl is an acid. Okay, understood? Now we have to understand one more thing, that in an acid base equilibrium like this, NH3 plus this equation, in an acid base equilibrium like this equation, uh, the forward reaction, that is formation of NH4 plus aqueous plus OH minus, and the reverse reaction, because that is what is this equilibrium. Reverse reaction means NH4 plus aqueous and OH minus getting combined to form NH3 and H2O back process. So both involve proton transfer. So in the forward reaction, we can say NH3 is accepting proton, so this is base, and H2O becomes acid. In the right side of the equation, when these two are getting combined to form NH3, NH4 plus, when it converts to NH3, it actually donates H plus, so it becomes acid here, and this becomes base because it is accepted. So on the left side, NH3 is a base, I will write it as base 1, H2O is an acid 1, and they give the products NH4 plus plus OH minus. But because it's a reversible reaction, the products are again converting back into reactants, and there is a dynamic. So when products are converting back, you go from this process to left, right to left. So NH4 plus to become NH3, it has to donate a proton. Therefore, it is an acid 2. And OH minus is accepting a proton and becoming H2O, so it is a base. So this particular thing, NH3 converting to NH4 plus and NH4 plus converting back to NH3. So this is one of the conjugate acid base pair. We call it conjugate acid base pair. So if suppose a question comes, what is the conjugate base of, similarly this is also a conjugate acid base pair, HCl and OH. So what is the conjugate base of H2O, sorry, not HCl, H2O. So what is the conjugate base of H2O is OH minus. What is the conjugate acid of OH minus? H2. Similarly, what is the conjugate acid of NH3? NH4 plus. What is the conjugate base of NH4 plus? NH3. So if we are talking about an acid, like let's say we can understand in the form of HCl reaction also. For an acid, I will write it here, conjugate acid base pair. For an acid, example, because in HCl case we cannot consider conjugate acid base directly because it is not a reversible. So we will take up this example only. So for an acid, what is the acid in this case on the left side? H2O. Okay. Conjugate base is OH minus or hydroxyl ion. And for a base, example NH3, conjugate acid is NH4. So an acid gives conjugate base by donating a proton. A base gives a conjugate acid by accepting a proton. That is the concept. So conjugate acid base pair consists of two species in the acid base reaction. If one of them is acid, then the product will be base. Vice versa. If the reactant is base, product becomes acid. And for an acid, its base conjugate base is found by removing one proton from the acid. For a base, its conjugate acid is found by adding one proton to the base. Okay. Now let's understand the HCl also. So let's write HCl gas plus H2O liquid gives H3O plus hydrogen aqueous plus chloride ion aqueous, right? So for HCl, this is acid, the conjugate base is Cl minus. For H2O, in this case H2O is acting as a base, its conjugate acid is H3O. So how do we know that? HCl is losing one proton to form Cl minus. Losing proton because HCl is an acid. And when it loses proton, it has formed a base, which is a conjugate. Similarly, water in this case is accepting a proton and becoming H3O plus. Therefore, water is a base because it is accepting a proton. Okay. Now, in this case, we also understand HCl is a strong acid. Okay. So, whenever its conjugate base we talk about, if acid is strong, so it has a weak conjugate base. Okay. And in this case, water is a weak base. Okay. Water is a weak base. So its conjugate acid hydronium ion is a strong acid. Understood? So not only that we are converting acid, and not only we are understanding acid base reaction, and we are also understanding conjugate acid base pairs, and we have seen that whether the original acid is strong, so its conjugate base will be weak. Whether the base is strong, in case of a base, its conjugate acid will be weak. And if the acid is weak, conjugate base will be strong. Base is weak, conjugate acid will be strong. Okay, got it? So similarly in this also NH3 aqueous. This is a weak base. This is a weak base. Therefore, its acid NH4 plus is a strong acid. Similarly, H2O in this case is a weak acid, and therefore its base hydroxyl ion is a strong base. Okay, so this is about the conjugate acid base and also the strength of those conjugate acids and bases. These are all concepts derived from Bronsted-Lowry concept of acids and bases. Okay, few more reactions are there mentioned in the book. You can follow them. Now, we also noted that through this both these examples, H2O is acting in one situation as an acid and in other situation it is acting as a base. Correct. So in the first concept, when we talked about HCl plus H2O, so here H2O is acting as a weak acid, weak base. In the case of HCl plus H2O, we discussed that H2O is a weak base because it is converting into hydrogen ion. So H2O is a base, whereas in case of NH3 plus H2O, H2O is acting as an acid. So H2O in one case acting as an acid, in other case it is acting as a base. So such compounds are called amphiprotic species. So in a particular reaction, it can take up a proton and become a base, like in this case, HCl plus H2O. In a particular case, it can donate a proton and become an acid, like in this case, NH3 plus H2O. So it is an amphiprotic species. So there are some other compounds like that. For example, carbonate ion. Okay. So whenever it is, I will just give the example of the carbonate ion also, so that in case it comes in the exam, you can understand it. So let us say hydrogen fluoride is an acid and it is reacting with HCO3 minus, okay, which is a hydrogen carbonate ion, not a carbonate, hydrogen carbonate ion. And how does it come about? NaHCO3, for example, okay, NaHCO3 has two ions, Na plus and HCO3 minus. You can understand it like that, right? Na plus and HCO3 minus, okay, and this HCO3 minus further disintegrates, okay. So basically, it disintegrates into Na2CO3 plus H2O plus CO2. This is the final reaction, but there is an intermediate reaction. Okay, so it will form Na plus plus HCO3 minus. Okay, which further disintegrates into this. So let's consider this hydrogen carbonate ion. So this hydrogen carbonate ion, if it reacts with hydrogen chloride, so it's a reversible reaction, and it will form H2CO3. So from HCO3 minus, it's taking on a proton to become HCO3, and when a proton is removed from HF, it becomes FF. And all these are aqueous. Okay, so I will mention it as AQ. Now in this case, HCO3 minus has taken a proton, so it's a base, but it's a weak base. Okay, because it's reacting. It's again converted like we discussed here. It's not stable, so it's a weak base. Similarly, HF is a very strong acid, so F minus is a weak base, a conjugate base. Okay. Now, in this case, we saw that HCO3 minus is acting as a base. Now, HCO3 converting into Na2CO3 is coming, right? So HCO3 minus can also act as an acid when it reacts with, let us say, hydroxyl ion, OH minus. So here I write NaHCO3, yeah, plus H2O you can write, and you can write it as hydroxyl ion and then convert it into this. Okay, plus H plus I will write. You can write like this. Okay. So here for this reaction, HCO3 plus can combine with OH minus, and it's also a reversible reaction. It's also a reversible reaction, and this yields CO3 2 minus. So from HCO3 you are donating a proton, so CO3 2 minus will come. All these are aqueous. Plus, what will OH minus convert into water? Now here, in the first case, HCO3 minus has accepted a proton and become H2CO3 aqueous. So it is a base. In this reaction, HCO3 minus has donated a proton and it became water. So sorry, it became CO3 2 minus. So this is acting as an acid. So again, this is amphiprotic species. So H2O, we gave an example. Then we also know HCO3 hydrogen carbonate ion is also an amphiprotic species. Okay, so this is the concept of Bronsted-Lowry in understanding acids and bases. In the next video, we will understand the Lewis concept.